Welcome along. In this first outcome, we're going to turn a bare list of numbers into a picture, building stem and leaf diagrams and box plots, and then reading the story they tell about the shape of the data and any odd values. Think about the last time someone handed you a spreadsheet with 200 sales figures on it. Your eye just glazes over, doesn't it? A good diagram fixes that in a heartbeat by answering 3 questions at a glance. Where's the data centered? How spread out is it? And is it lopsided? Across this outcome, we'll build 2 displays, the stem and leaf and the box plot, and use them to read features like skew and unusual values from real things such as exam marks or GP waiting times. Before we draw anything, let's get the vocabulary straight. A distribution is just the pattern of how often each value crops up. Raw data is the numbers in the order you collected them, and ordered data is those same numbers sorted smallest to largest, which is nearly always the first move. And frequency simply is how many times a value shows up. Here's the clever thing about a stem and leaf diagram. It sorts your data but keeps every single original value visible, which most charts throw away. You split each number into a stem, the leading digits, and a leaf, the final digit. So a mark of 41 becomes a stem of 4 and a leaf of 1. And you always add a key, something like 4, then a bar, then 1 means 41. Building one is a tidy 4-step routine. First, order all your values from smallest to largest. Then pick your stems, usually the tens digits, and list them down a column. Next, write each unit's digit as a leaf beside its stem, in order. And finally, never forget the key, spelling out that 4 bar 1 means 41. Let's look at 1 in action, with 20 exam marks. Each row gathers all the marks in that 10. So the 60s row reads 61, 62, 64, 66, and 67 all sitting together. The longest rows are where the marks bunch up, and here the 60s clearly dominate. Nothing is lost, every original mark can still be read straight off. And the key reminds you that 4 bar 1 means 41. Now let's read some summary values straight off those 20 marks, which run from 41 up to 92. The range is the highest minus the lowest, 92 minus 41, which is 51. With 20 marks, the median is the average of the 10th and 11th values, 64 and 66, so 64 plus 66 over 2 gives 65. The modal group is the 60s with 5 marks, and all of that tells staff the class performed solidly, centered around 65%. Here's a neat trick when you want to compare 2 groups. You share 1 column of stems and let the leaves grow outwards, 1 class to the left and 1 to the right. Say Class A's marks fan out on the left and Class B's on the right. Now you can eyeball center, spread, and shape together. You're comparing medians, ranges, and which side has the longer tail, all in a single picture. To describe spread properly, we chop the ordered data into quarters. The median, or Q2, is the middle value splitting the data in half. The lower quartile, Q1, is the median of the bottom half, so a quarter of the data sits below it. And the upper quartile, Q3, is the median of the top half, with 3/4 below. The gap between them, Q3 minus Q1, is the interquartile range, the spread of the middle 50%. A box plot draws that 5-number summary onto a number line, and once you know how to read it, you can size up a dataset in seconds. The box runs from Q1 to Q3 with a line inside marking the median. The whiskers stretch out to the smallest and largest values that aren't outliers, and any genuine outliers get plotted as separate points. Because the box spans Q1 to Q3, its width is exactly the interquartile range. Drawing 1 follows 4 steps. First, find your 5 numbers: the minimum, Q1, median, Q3, and maximum. Then draw the box from Q1 to Q3 with the median line inside. Add whiskers out to the lowest and highest values that aren't outliers. And finally, mark any value beyond 1.5 times the interquartile range as its own separate point. Let's put numbers on this using some real GP surgery waiting times: 11 patients measured in minutes. With 11 values, the median is the 6th one in order, which is 27 minutes. Q1 is the middle of the lower 5, 18, and Q3 is the middle of the upper 5, 36. So the interquartile range is 36 minus 18. That's 18 minutes, the spread of the middle half. Now picture that plotted. The box spans Q1 at 18 to Q3 at 36, with the median line at 27, and the whiskers reach the minimum of 12 and the largest ordinary value of 40. But there's a wait of 70 minutes sitting way out to the right, plotted on its own as an outlier. Notice the median sits left of center in the box, which is already hinting the data is skewed to the right. One very long wait stretching the tail out. So, which display do you reach for? The stem and leaf keeps every raw value, which is lovely for small or medium data sets, and it shows shape like a sideways bar chart. The box plot only keeps 5 summary numbers, but that makes it brilliant for comparing several groups at once. Both reveal outliers, one in the tails and the other as separate points. So it really comes down to whether you want the detail or the overview. Skewness is just a word for whether a distribution is balanced or leans to one side. If it's symmetric, both tails are roughly equal and the mean and median sit close together. Positive or right, skew means a long tail of high values pulling the mean up above the median, and negative or left skew is the mirror image, a long tail of low values dragging the mean down. Real data is hardly ever perfectly symmetric, so naming the skew is a proper interpretation skill. Picture 3 curves side by side: negative skew with its tail stretching left, a tidy symmetric hump in the middle, and positive skew with the tail reaching right. Incomes and house prices are the classic positively skewed example because a handful of very large values stretch the top end. Naming that skew tells you how honest the so-called average really is. Here's a handy rule for a positively skewed distribution. The mode is less than the median, which is less than the mean. Those few extreme values in the long right tail drag the mean upwards, while the median barely budges, which is why it's often the fairer average for skewed data. It's exactly why the Office for National Statistics reports median household income rather than the mean, because a few very high earners would otherwise flatter the typical figure. You can read skew straight off a box plot from where the median line sits. Bang in the middle with even whiskers suggests symmetry. Pushed down towards Q1 with a longer right whisker points to positive, right skew, and pushed up near Q3 with a longer left whisker means negative, left skew. Go back to our waiting times plot. The median sat left in the box, so we'd call that data right skewed. An outlier is a value sitting far out from the rest, and it can quietly distort your summaries. The standard way to flag one is the 1.5 times interquartile range rule. Anything below Q1 minus 1.5 times the interquartile range, or above Q3 plus that same amount, counts as an outlier. Those two cutoff values even have a name: the fences. Let's test our 70-minute wait properly. The interquartile range was 18, so 1.5 times 18 gives 27. The lower fence is Q1 minus 27, that's 18 minus 27, which is minus 9 minutes. The upper fence is Q3 plus 27, so 36 plus 27, which is 63. The value 40 sits comfortably inside the fences, so it's a normal reading, but 70 is beyond 63, so it's officially flagged as an outlier. It matters because an outlier might be a genuine extreme, a typing error, or a special case worth a closer look. That 70-minute wait could be a one-off emergency, a misrecorded figure, or a real sign of a struggling service. Outliers and skew both tug the mean and range away from the typical experience. So for skewed data, the median and interquartile range describe things more fairly. And the golden rule: never just delete an outlier. Investigate it first and report what you find. This splits our summary measures into two camps. The resistant ones barely flinch when an extreme value turns up, the median hardly moves, and the interquartile range ignores the extreme quarters entirely, so they're your go-to for skewed or outlier-heavy data. The non-resistant ones are the mean, which gets tugged towards a single extreme, and the range, which is defined by the two most extreme values, so keep those for roughly symmetric data with no nasty outliers. Let's pull it all together. Stem and leaf diagrams sort your data while keeping every value, and they always need a key. The 5-number summary becomes a box plot whose box width is the interquartile range. Skewness names the direction of the longer tail, positive to the right or negative to the left, and in positive skew, the mode is below the median, which is below the mean. And the 1.5 times interquartile range rule gives you fences to flag outliers, which you investigate rather than delete. That wraps up our first outcome on picturing the shape of data. If you'd like to go deeper, the reading list points you to friendly texts like Rowntree's Statistics Without Tears and Crawshaw and Chambers for the fuller treatment, plus the Royal Statistical Society's Significance magazine for readable, real-world articles. The Office for National Statistics website is well worth a browse for genuine UK distributions such as weekly earnings, and Corbett Maths and BBC Bitesize have handy-worked examples if you want more practice. Everything's on the Moodle for this unit, and do remember to reference our slides in your assignment.